Antimony is an essential industrial element, and it is almost entirely sourced from a single mineral, stibnite. These metallic, lead-gray crystals form deep within epithermal low-sulfidation environments and orogenic systems, precipitating out of boiling hydrothermal fluids. Finding these deposits is notoriously difficult. Stibnite veins are highly localized, structurally constrained, and almost always masked by heavy vegetation or thick sedimentary cover. Relying on a single exploration method to find them practically guarantees a drill core full of sterile rock. Isolating a viable deposit requires abandoning single-point metrics. Instead, we have to use multi-physics data fusion to map three distinct geological domains simultaneously: structural permeability, fluid alteration, and sulfide precipitation. This map displays the result of that fusion. To identify that single red star, the optimal drilling location, we have to process an immense volume of overlapping, visually chaotic data layers from satellites and ground sensors. The objective is to translate that chaos into a strict Boolean mathematical formula. We are looking for a specific spatial coordinate where 5 distinct physical anomalies perfectly intersect to define a Class A target. To understand exactly how that formula isolates the target, we have to construct the model from first principles, starting with a blank geological slate. Modern exploration does not look directly for the mineral. It maps the cascading, macro-scale physical disruptions that the hydrothermal system inflicted on the surrounding Earth millions of years ago. Every hydrothermal system requires structural permeability. Deeply buried, superheated fluids need a conduit, a fault, fracture, or shear zone, to migrate toward the surface. We map these conduits topographically using DEMNAS, a digital elevation model with an 8.3-meter resolution. The physical fracturing of the bedrock dictates how water erosion cuts across the surface, creating highly specific drainage patterns. Look at the drainage patterns in this atlas. Dendritic patterns indicate uniform rock, but parallel, trellis, or rectangular matrices indicate fault control. Water follows the structural grid. Between those streams, we look for a linear ridge. Ascending fluids deposit silica, creating a hard core that resists weathering. Topography alone only suggests a fault. To verify the physical roughness of the surface rock, we bounce C-band radar off it using the Sentinel-1 satellite. This matrix details the exact radar responses. The VV backscatter column measures vertical returns. High VV values isolate hard quartz outcrops punching through soil. Simultaneously, elevated VH backscatter and high GLCM texture flag chaotic returns, proving the host rock is heavily fractured. Intersecting DEMNAS and Sentinel-1 data mathematically confirms the physical plumbing of the fault system. However, a cracked rock is just a cracked rock. We still have to prove that corrosive, mineral-rich fluids actually flow through it. When high-temperature fluids ascend through these conduits, they chemically attack the host rock, creating a massive alteration halo that stretches far beyond the central vein. We map these chemical burn marks from orbit using Sentinel-2. By reading the visible, near-infrared, and shortwave infrared bands, we can detect the specific spectral signatures of the altered minerals. Satellites capture a tremendous amount of visual noise. To isolate exact alteration signatures, we run a principal component analysis, or PCA, which forces the target minerals to separate out mathematically from the background vegetation in soil. This table breaks down the PCA band formulas required to confirm the target. We need strict spatial zonation, an outer argillic cray halo enclosing an inner silicification core. On the map, the argillic halo renders as cyan, wrapping tightly around the bright white quartz stibnite core. We then run a secondary formula targeting iron oxides. This flags the Gaussian cap, the rusted, oxidized remnants of sulfides exposed to the surface atmosphere. Combining these layers into a single PC4, PC3, PC2 RGB composite provides a simultaneous view of the entire chemical geometry of the system. Spectral imaging confirms the fluid hit the surface, but a surface map cannot tell us how deep the trap goes, or if the internal structures are dense enough to hold a deposit. For that, we have to look underground. Penetrating the surface requires geophysics. We need to map the invisible physical properties of the rock itself to locate the specific subterranean trap where the stibnite precipitated. The first property is magnetism. As acidic hydrothermal fluids boil upward, they dissolve and destroy the primary magnetic minerals, like magnetite, embedded in the surrounding host rock. The RTP magnetic data shows the alteration zone as a broad magnetic low. This proves fluid presence, but it's too wide for drilling. We apply first horizontal and tilt derivative algorithms. These filter the blur, extracting sharp vertical boundaries around the demagnetized zone. To find the vein within those boundaries, we overlay gravity data. Gravity mapping measures the minute variations in subsurface rock density. This chart reveals the gravity paradox. The wide argillic clay zone we mapped earlier is less dense, creating a regional gravity low. The quartz and stibnite core, however, is exceptionally dense. It registers as a localized gravity high, trapped inside that broader regional low. By intersecting the sharp magnetic derivative boundaries with a localized gravity high, we pinpoint the exact structural trap. But a perfect trap is useless if it's empty. We still need to detect the metal. The final hurdle is differentiating a barren, sterile quartz vein from one heavily mineralized with economic grades of antimony. We have to send electricity into the ground. We use induced polarization and resistivity surveys as the definitive tools for detecting massive subsurface sulfides. This chart categorizes the required electrical responses. The silica core acts as an insulator, registering extreme resistivity between 500 and 3,000 ohm meters. We also measure chargeability. Sulfides act like capacitors, holding the charge to create an elevated IP signature between 30 and 60 millivolts. These two metrics must intersect. High resistivity with no chargeability means you found sterile quartz. High chargeability with low resistivity means you found scattered, uneconomic sulfides trapped in wet clay. The required profile is absolute: a highly resistive core wrapped in a low resistivity clay halo, punctuated by a central spike in IP chargeability. When extreme resistivity and high chargeability perfectly align within the structural trap, mapped by gravity and magnetics, the probability of encountering massive stibnite is maximized. A drill target is never found by chasing a single anomaly. It is defined by the strict Boolean intersection of all 5 physical layers. Parameter 1 requires a verified structural conduit, proven by Demnaz linear ridges and Sentinel-1 structural texture. Parameter 2 requires chemical evidence of fluid flow, proven by a Sentinel-2 silicification core wrapped in an argillic halo. Parameters 3 and 4 require a physical subsurface trap, proven by a localized gravity high caught inside a demagnetized corridor. And parameter 5 requires confirmation of the metallic payload, proven by the precise alignment of extreme resistivity and high chargeability. Removing even a single parameter from this equation exponentially increases the risk of drilling hundreds of meters into barren rock. When all 5 layers align perfectly on a single map coordinate, the workflow is complete. That coordinate is the target Antimon Class A. Modern geophysical exploration mathematically eliminates absolutely every location the ore cannot be until only the undeniable target remains.